It shouldn't have survived. 18,000 tiles, cracked and leaking after diving through plasma over 1,500 degrees Celsius. But it did. SpaceX says, quote, "We got all the heat shield data we needed, and then some. Some call it a failure. SpaceX calls it a win." So which one is true? Because Starship's new plan for a fully reusable rocket depends on the answer. Stay with me. Here's the situation. Starship's heat shield came back from Flight 13 covered in more coolant leaks than the one before it. Not fewer, more. On paper, that sounds like a step backward. A rocket program claiming progress while showing you a worse-looking heat shield. So let's slow down and look at exactly what happened, tile by tile. During re-entry, the ship punched through plasma at temperatures above 1,500 degrees Celsius. That's hotter than the surface of Venus, hotter than lava fresh out of a volcano. For about 50 minutes, the underside of Starship sat inside a wall of ionized gas, glowing white-hot, while the rest of the vehicle tried to stay in one piece. And this time, SpaceX wasn't flying blind. They added load sensors to the tiles themselves, tracking stress in real time as the ship climbed to orbit. They painted select tiles white, so satellites could photograph the heat shield's condition from space, mid-mission. They even bolted new tiles onto the aft flaps, testing an attachment method that had never flown before. So the question worth sitting with is this. If SpaceX added all this new instrumentation, and the heat shield still came back leaking more than the last flight, did they fail, or did they just get better at seeing the damage that was always there? To answer that, you need to understand what a coolant leak on Starship actually is. And this is where most coverage gets it wrong. This isn't a broken pipe. It isn't a crack letting fuel spill out. Think of it more like sweat. Your body cools itself by pushing moisture through your pores, letting it evaporate and pull heat away from your skin. Starship's tiles work on a similar transpiration principle in the gaps between them, releasing small amounts of coolant to manage extreme heat spikes at the seams. When engineers say leak, they mean the coolant is escaping faster or in places it wasn't fully sealed to handle yet. It's a sign of stress, not necessarily a sign of failure. Now layer in the second detail. Flight 13's ship, S-40, faced friction waves peaking around the 50-minute mark of re-entry, exactly when aerodynamic heating hits its ceiling. That's the moment engineers watch closest, because it's the moment tiles are most likely to crack, shift, or vent coolant. And the tiles did all three. Some cracked, some leaked more visibly than on Flight 12. A few showed hairline damage close to fresh phone screen cracks, but there's one detail almost nobody mentions. Compare that to the space shuttle. NASA's shuttle used roughly 24,000 unique heat-resistant tiles, and after nearly every single flight, ground crews spent months, not hours, inspecting and replacing them by hand. Some tiles took specialized labor because no two were identical. Starship carries around 18,000 tiles too, but SpaceX is building them to be interchangeable, machine installed, and repairable within hours, not months. So when this video says damage happened, that's true. But the meaningful number isn't the crack count, it's the repair time. Which raises the question that actually matters for this whole program. Is fast repair actually possible at scale? Or is that still a promise waiting to be proven? What a cracked tile actually costs. Let's follow the money and the mission, because that's where this story escalates. Every hour Starship spends grounded for tile repairs is an hour it isn't flying, and the entire economic case for Starship depends on turnaround speed. SpaceX has talked about eventually cutting launch costs from thousands of dollars per kilogram down into the tens of dollars per kilogram range, an ambitious target the company hasn't hit yet. That target only works if Starship flies again within days, not months, the way an airliner does. A rocket that needs a 6-month heat shield overhaul between launches isn't a spacecraft anymore. It's an expensive museum piece that occasionally leaves the ground. So when Musk says, quote, "We got all the heat shield data we needed, and then some," that statement carries more weight than it sounds. It means engineers now have hard numbers on exactly where tiles crack, exactly where coolant escapes fastest, and exactly which tiles are the weak points. That data doesn't fix the heat shield today, but it tells SpaceX precisely where to reinforce it before Flight 14. And Flight 14 is where the stakes jump. Musk has already said that unless the mission data review turns up a serious problem, SpaceX will attempt something it has never done before on this vehicle. Catching Starship out of the sky with the launch tower's mechanical arms, nicknamed Mechazilla, not landing on legs, not splashing into the ocean. Catching a returning spacecraft mid-air, the way you'd catch a foul ball, except this ball weighs hundreds of tons and is still radiating heat from reentry. Think about what that means for the heat shield specifically. A splashdown forgives mistakes. The ocean is soft. A tower catch does not forgive mistakes. If the ship arrives with warped tiles, an uneven heat profile, or unexpected structural flex from coolant loss, that error shows up as a catastrophic collision with a multi-million-dollar tower, not a wet landing in open water. Flight 13's tile data isn't just a report card. It's the safety margin for the most dangerous maneuver Starship has ever attempted. This is where the story gets more interesting than a simple pass or fail grade on one flight. Buried in the flight updates is a detail about a new nose cone spotted inside the Star Factory, painted white, visibly different from the current design. SpaceX hasn't confirmed exactly what changes it represents, but put it next to everything else happening at once. Load sensors added mid-flight, satellite tracking of tile condition, aft flap tiles testing new attachment hardware, and now a visually distinct nose cone under construction while Flight 13's ship was still floating in the ocean. That's not a company patching one heat shield. That's a company already building the next version of the vehicle before the current one has even finished its post-flight inspection. Flight 13 wasn't the finish line. It was a live data collection run for a heat shield generation that hasn't been unveiled yet. And that reframes the entire coolant leak story. The tiles on S40 weren't necessarily supposed to survive perfectly. They were instrumented specifically to fail informatively, to tell engineers exactly where the next design needs reinforcement before it's committed to metal. Every additional leak, every crack, every stress reading from those new sensors becomes an input into a heat shield SpaceX hasn't shown the public yet. So which is it? Is Flight 13 a heat shield success because it survived reentry and delivered usable data? Or is it a heat shield that's already obsolete, replaced in engineering terms before it even splashed down? Both things can be true at once, and that tension is exactly what makes the next 12 months of Starship development worth watching closely. SpaceX has broken things before on purpose. Before we go further, it's worth remembering how SpaceX got here in the first place, because this isn't the first time a failure turned into the foundation for a breakthrough. Look at Falcon 9. The first attempts to land an orbital booster back on Earth ended in explosions, repeatedly, on live television, in front of millions of people. One booster tipped over after landing. Another ran out of hydraulic fluid mid-descent. Another hit a drone ship so hard it became a fireball that SpaceX later nicknamed, with a straight face, a rapid, unscheduled disassembly. At the time, critics called it a stunt that would never work, an expensive way to blow up hardware for headlines. Today, Falcon 9 boosters land routinely, sometimes multiple times a week, and SpaceX has reflown individual boosters more than 20 times each. That history matters here because the same pattern is playing out with the heat shield. Coolant leaks and cracked tiles look like setbacks in isolation, but SpaceX's entire development philosophy is built on flying hardware to the point of failure, on purpose, faster than competitors are usually willing to risk, specifically to find the failure points nobody could predict from a simulation. A cracked tile in this context isn't necessarily bad news. It's a company doing exactly what it did with Falcon 9, just one flight closer to solving the next hard problem. Does that guarantee Starship's heat shield gets solved as cleanly as Falcon 9's landing legs did? No, nothing about spaceflight guarantees anything. But it does mean the coolant leaks in this video aren't the end of a story. They're the middle of one. SpaceX has already proven, at least once, it knows how to finish. Now, to be fair to the doubters, not everything about this heat shield story is reassuring, and it's worth saying that plainly instead of glossing over it. 18,000 tiles is an enormous number of individual points of potential failure. Even if the failure rate per tile is small, small percentages multiplied across 18,000 parts still produce real damage on every single flight, and that damage has to be caught, diagnosed, and fixed correctly every single time, with zero tolerance for the kind of mistake that goes unnoticed until the next reentry. Unlike an airplane, which can abort a flight and land safely if something goes wrong mid-air, a Starship heading back into the atmosphere with a compromised heat shield has very few options if the damage turns out to be worse than the inspection caught. There's also the matter of scale versus speed. SpaceX is trying to compress a testing and refinement process that traditionally took NASA and its contractors years, sometimes over the course of an entire space shuttle program, into a handful of Starship flights. That's either a genuine engineering breakthrough in how fast a heat shield can mature, or it's a timeline that's going to keep slipping every time a new problem shows up. The same way Flight 13 showed up with more leaks, not fewer, compared to Flight 12. So the honest answer sits between blind optimism and outright doubt. The data from Flight 13 is real progress. The unresolved risk is also real. Both of those things can be true heading into the next launch, and pretending otherwise in either direction isn't an accurate picture of where this program actually stands. Why orbit changes everything. This is the part that should worry anyone assuming the hardest challenges are behind Starship. Every flight so far, including Flight 13, has flown what's called a suborbital trajectory. The ship goes up, arcs across an ocean, and comes back down within roughly an hour. That's already brutal on a heat shield, but it is nowhere close to the heat load Starship will face once it actually reaches orbit. An orbital re-entry means a longer free fall from a higher altitude, a longer exposure window inside the plasma layer, and a heat shield that has to hold its integrity for a return trip that isn't measured in 1 hour, but in a much longer, much hotter descent. Picture the difference between briefly touching a hot stove and holding your hand against it for several times as long. The tiles that survived Flight 13 with cracks and coolant leaks were tested against the easier version of this problem. Orbit is the harder version, and it's coming next. That's the piece missing from most reactions to Flight 13. People are grading this heat shield against yesterday's test. SpaceX is already grading it against tomorrow's mission, one where the ship travels across the Indian Ocean, continues over the Pacific, and returns to its launch site after a much longer, much higher altitude re-entry. The coolant leaks you saw in the footage weren't the final exam. They were the practice round for an exam that hasn't been written yet. Here's a way to put a number on that gap. Re-entry heating scales dramatically with speed, not in a straight line, but closer to a steep curve, meaning even a modest increase in orbital velocity translates into a much larger jump in the total heat energy the tiles have to absorb and shed. A suborbital hop like Flight 13 loses most of its speed gradually, over a long arc, before it ever reaches the thickest part of the atmosphere. A true orbital re-entry comes in faster, steeper, and holds that peak heating window open longer. So when this heat shield eventually flies an orbital mission, it isn't facing a slightly harder version of Flight 13. It's facing a fundamentally more demanding thermal environment, one where every crack, every coolant leak, every weak seam identified. This time becomes the difference between a tile system that holds and one that doesn't. The number nobody's saying out loud. Let's put this in perspective with one more comparison, because it changes how you should feel about cracked tiles as a headline. Out of roughly 18,000 tiles covering Starship's underside, the cracked ones represent a small fraction, not a widespread failure across the vehicle. SpaceX has said these tiles can be swapped out in hours, not weeks. If that repair claim holds up at scale, and it hasn't been fully proven yet under real operational pressure, then a handful of cracked tiles isn't a disaster story. It's routine maintenance, the same way an airline replaces worn brake pads without grounding its entire fleet. But that word, if, is doing a lot of work in that sentence. SpaceX has never repaired and reflown a Starship on a rapid turnaround timeline. Every flight so far has ended with the vehicle either destroyed, discarded, or floating in the ocean for study, not refurbished, and relaunched days later. So the real test isn't whether the tiles can theoretically be swapped fast. It's whether SpaceX can actually do it under time pressure with a launch tower waiting and get it right the first time it matters. That's the gap between promise and proof. Flight 13 strengthened the promise. It did not yet deliver the proof. Zoom out for a second because it's easy to lose the bigger picture in tile counts and coolant numbers. If Starship's heat shield problem gets solved in the way SpaceX is describing, this isn't just about one company's rocket getting slightly better. It's about whether humanity's access to space gets fundamentally cheaper. Right now, launching mass to orbit costs thousands of dollars per kilogram. A fully reusable Starship, one that flies, lands, gets a quick inspection, and flies again within days, could push that cost down by a wide margin, by a factor of 10 or more, according to SpaceX's own long-term projections. That kind of shift doesn't just help SpaceX. It changes what's financially possible for satellite constellations, for research missions that current budgets can't touch, and for the long-term goal of sending enough mass toward the moon and Mars to build something that actually lasts there. None of that happens without solving exactly the problem Flight 13 exposed. A heat shield that survives re-entry once is a science experiment. A heat shield that survives re-entry, gets inspected in hours, and flies again next week is a transportation system. Right now, Starship is still somewhere between those two states, closer than it's ever been, but not there yet. So where does that leave the plan going forward? SpaceX now has tile-by-tile stress data from a real re-entry, satellite imagery of a heat shield in near real time, and a nose cone in production that suggests the next design iteration is already underway. The company is preparing to attempt its riskiest maneuver yet, catching a returning Starship out of the air, using a heat shield that just proved it can survive re-entry, but not yet proven it can survive re-entry cleanly, without cracks, without extra coolant loss, without any margin for error at the tower. That's the tension heading into Flight 14. Not whether Starship can come back from space, it's already done that. The real question is whether it can come back clean enough, consistently enough, to be caught, repaired in hours, and sent back up again like it's just another Tuesday. And that answer doesn't come from a press release. It comes from the next flight. That's the data. Flight 14 gives us the verdict. Thanks for watching. I'm Adrian. Like, share, comment, subscribe to the Space Brief, and check the video right on your screen now.